today I'll be talking about the Galileo spacecraft. Now this video is a part 1 in a series. Today I will be talking about the instruments on board the Galileo spacecraft. Now the Galileo spacecraft was a spacecraft sent to observe Jupiter and its moons. Okay, so now let's talk about the instruments on board the Galileo spacecraft. The first one we will talk about is the magnetometer. The magnetometer was used to detect the strength of the magnetic field of celestial objects that the Galileo spacecraft would visit. So the strength of a magnetic field is measured in teslas or gauss, where 1 Tesla equals 10,000 gauss. Now, the strength of an average refrigerator magnet is around 0.001 to 0.005 teslas, or 10 to 50 gauss. Now, you won't believe this, but the Earth's magnetic field is around 0.00003 to 0.00006 teslas, or 0.3 to 0.6 gauss, depending on where your location is. So the Earth's magnetic field is less. The strength of the Earth's magnetic field is less than the strength of an ordinary refrigerator magnet. And that is why if you held a paperclip in the air, you won't feel like the paperclip is attracting to the Earth. The force that brings your paperclip down to the surface when you drop it is gravity, not magnetism. Now, Jupiter's magnetic field is around 0.00042 to 0.0014 tesla, so 4.2 to 14 gauss. This is around 20 times the magnetic field of Earth, but still not as strong as a refrigerator magnet. So our next instrument on board the Galileo is the low-gain and high-gain antennas. Okay, so there are 2 types of antennas. We have receivers and transmitters. Receivers take in radio signals and convert them into electrical signals for other uses. Transmitters convert electrical signals into radio signals. Now, sometimes we want to increase the power of the signal we are transmitting. So for a receiver, we want to increase the power of the electric signal. And for a transmitter, we want to increase the power of the radio signal. If this was an electric circuit, we would be using an amplifier. But this is an antenna. We can't use an amplifier, however, for transmitters, we can concentrate the signal in one direction. And for receivers, we can take in radio signals from only one direction. To understand why this increases the power, let's look at a simple analogy. Let's say you have a flashlight and you're standing in a dark place. You switch on your flashlight and you have a ray of light coming from your flashlight. Now let's say that there's a ghost standing right in front of you. You can see all around you now, but you can barely see the ghost. You focus your flashlight now, and you can't see all around you, but you can clearly see the ghost. So a low-gain antenna is kind of like the first example. Your flashlight wasn't focused enough. A low-gain transmitter can send signals in all directions, but not very far. A low-gain receiver can receive signals from all directions, but not all the signals coming towards it. A high-gain antenna is kind of like the focused flashlight. A high-gain transmitter can send signals in one direction, and these signals can go far. They can go very far, and they're very powerful. A high-gain receiver can receive signals from only one direction, but it receives most of the signals coming towards it. So for most Earth-orbiting satellites, low-gain antennas are used. They can send and receive simple information, so they're ideal for Earth-orbiting satellites. For high-gain antennas are often used in space probes venturing to the outer solar system. So the high-gain antennas need more precise aiming. Okay, so our next instrument is the radioisotope thermoelectric generator. Now, the radioisotope thermoelectric generator is a pretty complicated name, but you can already figure out from the generator part that we're dealing with the engine of the Galileo spacecraft. So let me explain. This is a hydrogen atom. It's got an electron, which has a negative charge, and a proton, which has got a positive charge. Now, these are called subatomic particles. But there's actually 3 subatomic particles. We have only 2 ones, an electron and a proton. We have another subatomic particle called the neutron. Now, a neutron, it has a neutral charge. It's not negative, not positive. But when we add a neutron, this is not hydrogen anymore. Hydrogen has one proton and one electron. This has one proton, one neutron, and one electron. However, the periodic table is organized based on the number of protons in the element, called the atomic number. So this has nothing to do with the number of neutrons in the element. So technically, this is still hydrogen. So what do we call this? Well, we can call this an isotope of hydrogen. An isotope is a different form of an element where only the number of neutrons differs between the forms. So a normal hydrogen atom can also be called protium. Protium has one electron and one proton, no neutrons. So over here we have the symbol for protium. So the one on the top basically means the number of protons and neutrons in the atom. So we have one proton and 0 neutrons. 1 plus 0 equals 1, so we place a 1 there. The other one means the number of protons only, or the atomic number. So we have 1 proton here, so we put a 1 there. Now, when we add a neutron, we call it a deuterium. Now, the 2 again means the number of protons and neutrons. Here we have 1 proton and 1 neutron. 1 plus 1 equals 2, so we place a 2 there. The 1 on the bottom is also the amount of protons or atomic number. Now, for a hydrogen isotope, the number on the bottom, the atomic number, will always be 1 because hydrogen has an atomic number of 1, and all of its isotopes, the atomic number does not change, only the number of neutrons. So our next one is tritium. Tritium has got 3 subatomic particles in the nucleus. So the subatomic particles in the nucleus are basically the protons and neutrons. So we put a 3 on the top. Then on the bottom, we will again put the number of protons, which is 1. Okay, so that explains the isotope part. But what about the radio? Just before the isotope. Well, that basically means that we're dealing with a radioactive isotope. So what do I mean by that? Well, let's take an example. Tritium, an isotope of hydrogen, is a radioactive isotope. And the reason why is because it's very unstable. So because it's unstable, the subatomic particles in the nucleus are jiggling around. And when they jiggle around, they produce energy or radiation. And this produces heat, which can then be used to produce electricity. Okay, so in the Galileo spacecraft, we use plutonium-238, which is an isotope of plutonium, and it has 94 electrons, 94 protons, and 144 neutrons. So that is a lot of subatomic particles. Okay, so our next part is the Jupiter atmospheric probe. The Jupiter atmospheric probe, which was attached on the Galileo spacecraft, was designed to land on Jupiter. By doing so, the Jupiter atmospheric probe became the first spacecraft to enter Jupiter's atmosphere. It discovered that Jupiter had enormous storms. The pressure was so intense, the Jupiter atmospheric probe was crushed, then melted, and then vaporized. Okay, so thank you for watching. You can watch my Cassini-Huygens Space Mission Part 1 and Cassini-Huygens Space Mission Part 2 videos over here. And don't forget to subscribe and like this video. Bye!